Good morning, everyone. This is Matt Shergalis, Marketing Manager for the National Steel Bridge Alliance, and I'd like to welcome you all to today's webinar on metallizing. For today's webinar, we have two presenters. Presenter number one is Brian Raff. He's the Director of Marketing for Can-Am Bridges, where he provides strategic leadership in the execution of Can-Am's national marketing programs. Prior to joining Can-Am, Brian spent nearly a decade with AISC in a variety of business development and marketing roles. He holds a bachelor's degree in architectural engineering from Penn State and an MBA from DePaul University. Also with us today is Tony Matudis, who is the National Sales Manager for Can-Am Bridges. He has over 30 years of bridge experience in a variety of managerial and executive positions. With that, I'd like to welcome Brian and Tony and turn things over to them.
Thanks a lot, Matt. Appreciate the introduction. First, want to certainly thank NSBA for the opportunity to give this presentation on metallizing, and I'd like to thank you all for attending. I think it's a good time to discuss some of these important issues related to corrosion protection in the bridge industry. In recent years, we've been dealing with an increased interest in metallizing. So states are looking for long-term solutions to protect their assets. Certainly, life cycle issues have always been a consideration. So now we're going to look at ways that metallizing can address these. So over the next 44 slides, Tony and I are going to cover some of the basics of metallizing. Through the presentation, you'll learn about the technology, what's needed. Basically, we'll discuss a lot of these items at their most basic level. We'll go into the process of how it's applied and the keys to achieving good quality coating. We'll talk about some of the materials that are used and why they're chosen. Then Tony's going to go into some of the project examples and discuss why metallizing was chosen over other options. We'll talk about slip-critical connections and how they relate to metallizing. We'll cover where the steel bridge industry is at in terms of metallizing, what we're doing looking toward the future of metallizing. Then we'll have some time for questions and answers. So again, 44 slides. We should get through these in about 50 minutes or so, and we'll have plenty of time for some questions and answers. So if you think of anything, please go ahead and write it into the chat box. So why are we even talking about metallizing? Why are we having this conversation? Well, there's two givens in bridge construction. Concrete cracks, steel corrodes. Fortunately, we've got something to deal with steel corrosion. Certainly, there's a whole wide range of corrosion protection options available. You've got paint, galvanizing, metallizing, all sorts of options. And owners are looking for longer life and longer maintenance cycles. So we're seeing the emergence of metallizing as a viable option in more recent times. All corrosion protection options have their pluses and minuses. One solution isn't always the best. It obviously depends on a whole lot of different factors, so we're going to discuss a lot of those. But since today we're talking about metallizing, we'll go over some of the benefits that metallizing can offer, and we'll discuss those in further detail as we go through the presentation. But just as a couple of key bullet points before we begin, metallizing has no size or shape limitations. Essentially a line-of-sight spray application, so you're not limited to the length of a galvanizing kettle. As big as it is, doesn't really make any difference. You can metallize it. 2, it's a cold process. That means the steel never reaches more than 250 or 300 degrees, so there's no curing or cooling time. This helps increase throughput through the shop and helps to minimize the impact on schedule. There's no volatile organic compound emissions, so it's a safe process, and all the excess zinc can be collected and recycled. And finally, with limited maintenance, you can essentially achieve an indefinite life cycle of the bridge. And we'll go over what limited maintenance means as we move along through the presentation. So let's take a look at what metallizing is and how it works. Metallizing is just another name for a general term of thermal spray coating. Thermal spray coating, and in our case, specific to the bridge industry, again, it's just a line-of-sight application using zinc or aluminum in a wire or powder form. The zinc-based spray-on coating provides two types of protection. One is a barrier protection, and that's similar to any other type of coating you'd find in either paint or galvanizing. Essentially, the hardened zinc provides a protective barrier over the steel, preventing any items from beginning the corrosion cycle. But second, and probably the most important, is the fact that metallizing, certainly with zinc, provides galvanic protection. Metallizing is effective because the spray-on zinc sacrifices itself to protect the steel. The sacrificial protection is like the protection provided by zinc-rich primers or galvanizing. And essentially, this is really the reason why we use it, because if there's any occurrence of damage or any place where steel is exposed, the zinc will sacrifice itself in order to protect the substrate. In the bridge industry, arc spray is the most common form of applying metallizing. And what you're seeing here above is just a static depiction of what the internal workings of an arc spray application gun look like. Through arc spray, two electrically opposed wires, which you see in yellow, they're fed through the gun, similar to what you'd find in a welding machine. Because of their strong opposing charges, an electric arc forms at the intersection. The heat from the arc melts the wire, and the molten metal, either zinc or aluminum or a mixture of the two, is propelled onto the steel girder by jets of compressed air. Flame spray is another application method that has been used in the past, although I would say it's kind of a more archaic method. It's really not used too much in the industry anymore. Primarily what you'll find as the dominant application format is arc spray, or otherwise known as twin arc spray. So what's a coating without talking about blasting requirements? I think that we'd all agree that getting a good surface profile and good surface preparation is probably the key to getting good adhesion for almost any corrosion protection option. ASTM requires a minimum of SSPC SP10 near white finish. Blasting can be done either semi-automated or by hand, depending on the available equipment. In this case, what you're seeing in the picture here is somebody blasting the steel girder by hand to provide the necessary profile for a metallized surface. And that's actually a different type of profile that you would expect to find for a coated or painted surface. So I'm going to show you this short little video of what it looks like to hand blast a steel girder in preparation for metallizing. So in order to get the proper adhesion for metallizing specifically, the steel really needs to take on what we call an angular, sharp anchor tooth profile. This is really the key to getting good performance out of a metallized surface. The reason why the angular profile is so important is metallizing is a coating that relies on a mechanical bond between zinc and the steel substrate. Ideally, we'd love to get about 3.5 mils of profile depth. 2.5 mils as a minimum is really the necessary requirements in order to get good adhesion. Good roughened surface with pronounced sharp angular peaks and valleys provide a good surface for molten spray to adhere to. This mechanical bond is similar to other types of coatings like paint, which also rely on the surface area of the profile. What's really important to understand, though, is here in this case, this adhesion process is very different from galvanizing, which forms an alloying layer of zinc, iron, and steel. So when galvanizing, zinc is metallurgically bonded to the steel, essentially becoming a part of the steel itself. So it's not really a coating, and that's the difference. Galvanizing actually becomes part of the steel. Metallizing is different because you're relying on adhesion strength through the surface preparation of the profile. So there is a difference between steel shot and steel grit. All blast material really isn't the same, and it's important to make that distinction when we're talking about metallizing. Abrasive blast cleaning is a really important step to treating steel before applying any coating. It's generally accepted that blasting is the most important factor, again, to the success of any corrosion protection system. Typically, blast cleaning removes any of the mill scale, rust, oil, grease, and other contaminants that the steel may accumulate through the production and transportation process. What you're seeing on the left is a picture of round steel shot, and this is typically used to prepare a surface for painting, and the surface profile you'll typically get is a peened or a dimpled profile, so it's really not that sharp angular profile we're looking for. The picture on the right is depicting some steel grit, and you can kind of tell just by the shape of the grit, it's really sharp and angular. It's got corners of its own that really bite into the steel as it's blasted. So with the right velocity, some mixture of round shot and steel grit are necessary in order to achieve the proper surface profile for metallizing. So Tony and I have given a presentation on metallizing quite a bit, and one question that comes up quite often is about temperature and whether that has any effect on the ability to metallize. Temperature consideration is more applicable to painting, but it really doesn't have any effect on the ability to metallize. So most of the steel fabrication shops are going to control their humidity and their temperature anyway. So it's kind of a moot point. In the field, certainly temperature with other coating processes make a difference, but temperature really has no effect on our ability to metallize, even if it's out in the field. What is important to keep in mind, though, is temperature and humidity does affect the time that a fabricator or your third-party thermal spray coating applicator are allowed between blasting and coating. So it depends on the difference in specifications. Each state may require different things. Contract documents should ultimately specify the amount of time between blasting and coating. In our own shops at Can-Am Bridges, we feel comfortable with an 8-hour window between blasting and metallizing, but again, this is all dependent on where a shop is located and some of the geographic conditions or the atmospheric conditions that could affect the amount of time it would take for flash rust to start blooming. So just keep that in mind. So I'm going to show you an animation of what the inside of this application gun looks like through the metallizing process. Again, we kind of talked about the wires and the compressed air. This should hopefully give you a better sense for what it looks like. You can see as this thing rotates and breaks down, you can see those yellow diametrically opposed wires feeding into the gun. As soon as they strike each other, that arc forms and basically vaporizes that zinc or aluminum or alloy into molten material, which is then propelled onto the steel by compressed air. This next slide will show you what's happening on the surface of the steel and how those splats cool. Let me show you this video as I talk. So this high spray velocity is key to penetrating that anchor tooth profile. Again, in this image here, you can kind of see it's not a smooth or dimpled surface. This is really a sharp angular profile. So the particles get locked into those ridges of the profile when they cool. I know splat sounds kind of like a funny word, but it's actually a recognized term to describe what's happening with the molten droplet of zinc or alloy that strikes the surface, flattens, then solidifies. And this is really an important distinction. This is sort of the mechanism for how metallizing works. Imagine a series of these splats hitting the steel. So once they're molten, they hit the steel and they flatten out. These splats overlap one another to form a protective armor that resembles the scales of an armadillo. So you can kind of picture what this is looking like on a more microscopic level. In essence, the overlapping effect of these zinc scales or splats essentially is what protects the steel from corrosion, and this is really what the metallizing process boils down to. So both blasting and metallizing can be either hand-applied or semi-automated depending on the type of equipment available. I would say for the most part, at least to get a really nice and even surface through metallizing, semi-automated is a good way to go. However, I will say that in order to get the right profile for blasting, you'll typically find that hand blasting is the dominant method for achieving the profile. And it's also important to keep in mind that that's not a quick process. That actually, it's a pretty lengthy process that takes some time. So something to consider when choosing your corrosion protection options. The only counter to that, I would say, is because it's a cold process and it's not a coating like paint, you don't have to wait for anything to dry or cool or cure. Basically, once that zinc solidifies on the steel, you can touch by hand and inspect it immediately. So that cuts down on the schedule and allows us to get a lot of girders through the shop quite quickly. Again, it's a cold process, which we talked about. The steel never exceeds 250 to 300 degrees. But what's also important to mention here is that there's no risk of weld damage or no curvature or camber distortion that you can sometimes find when galvanizing. So where are we in terms of industry trends specific to third-party versus in-house metallizing? Again, we're talking about this now because I think we're at a place where there's been a pretty dramatic increase in interest. 10 years ago, metallizing wasn't really even discussed. I mean, maybe it was kind of the exception to the rule. It still occurred, just not at the frequency that it does now. Fast forward 5 years, and there was a pretty substantial interest. Things were starting to ramp up a little bit. And currently, I think metallizing is becoming a more common corrosion protection option. A lot of states have interest in it. There's several states that have their own specification, and we'll kind of get into that as we move further into the presentation. But as far as I know, there's only a few fabricators with dedicated staff, dedicated equipment, and all in-house metallizing capabilities that are able to handle the demand and increase for all these metallizing services. I think that what you're going to find over the next couple of years certainly is as metallizing generates a bit more momentum and states are finding that they can get a longer lasting, more durable coating, I think you're going to find more fabricators looking into the technology, ramping up that learning curve, and I think metallizing will become even more competitive in a couple of years than it is now. The question comes up pretty often about, what do I look for in terms of selecting the right applicator? What kind of things do I need to look for? There's a bunch of ways to really look at it. I mean, you can ask somebody to provide you with a number of square footage that they metallize in a year. You can ask them to show you some test panels. You can certainly ask for references and find out how previous jobs went, project examples with technical details. It's obviously up to the engineer of record to define what that criteria is. I think what the most important thing to look for is you just want to make sure somebody's been applying metallization in a continuous manner over the course of a period of time. You don't want somebody metallizing 1 or 2 bridges a year, with open windows of time between them. As long as you're comfortable and they can show you that they have a pretty good experience with continuous metallizing, I think you're in good shape. So we'll talk about some of the consumables and some of the materials that are used for metallizing. There's really only 3 flavors that metallizing come in for the bridge industry specifically. That's 99.9% zinc, or I'll refer to that as pure zinc. You've got 85% zinc, 15% aluminum alloy, which is what we'd refer to as 85-15, and then you've got 99.9% aluminum, or pure aluminum. It's important to note that these are really specific to the bridge industry. When you get outside of that into manufacturing and electronics and all that kind of stuff, they can metallize essentially any type of metal. You see copper and tin and all sorts of other things. So, metallizing is a bigger industry, but in our own context, we're really looking at zinc and aluminum. Another important note, or even a tip, is metallizing wire doesn't fall under Buy America requirements because it's not iron or steel. So we'll talk a little bit about the differences between zinc and aluminum, and then we'll get into specifically how they relate to metallizing. So there are a couple of questions you need to ask when determining which material you want to use for your consumables. Project location is obviously a very important thing to think about. Is your project located in the northern areas where they're going to deal with a lot of ice and snow and road salts? Is it in a dense industrial or manufacturing sector where you've got a lot of chemical components in the air? What about coastal or marine environments? These are all questions you'll need to think about as you're selecting your material or specifying. So when it comes to temperature, it's kind of interesting, right? So on Earth, the highest recorded temperature ever on Earth is 136 degrees Fahrenheit, or 58 degrees Celsius for my Canadian friends. Coldest temperature ever measured on Earth was negative 126 degrees Fahrenheit, or negative 88 degrees Celsius. That seems extreme for us, obviously, as living organisms, but it doesn't seem so extreme when you're thinking about how things perform outside, and certainly the durability and longevity of steel. So what's important to remember is metallizing is used outside to protect bridges. So it really only needs to handle temperatures from, again, minus 30, minus 40, minus 50 at the most in Fahrenheit, up to maybe 120 degrees Fahrenheit on the hot end. This is where this distinction comes into play, because as you add aluminum, it's able to resist much higher temperatures that you would see in, for example, furnaces and boilers and things of that nature. So zinc and aluminum, certainly both viable options for the bridge industry, but again, keep these temperatures in context as we go through some of these materials more specifically. And finally, the question, is pH a factor? And finally, number 4, can you achieve the required surface preparation? The answer for bridges is yes. Right, you've got a girder in the shop. It's in an open space where you can get your application gun or fit your blast cabinet and everything. That's not an issue. The reason why this question is posed, and again, to give you context, is there are other things in other industries that get metallized, like tanks and boilers and all these things. Can you actually get the gun in there to metallize? So just some things to think about sort of on a broader perspective. Now, when we talk about specific consumables for metallizing in the bridge industry, we'll start with zinc wires. So 99.9% zinc wire manufactured per ASTM B833. If you remember from the beginning of the presentation, zinc provides galvanic protection, and it actually provides a bit more galvanic protection than aluminum. Its greater galvanic power protects gaps in the coating better than pure aluminum, and it's marginally easier to spray pure zinc than it is pure aluminum, and this is something we found in our own experience. Zinc tends to be easier to spray, and it certainly seems to be easier on our equipment. I would say aluminum kind of beats up our equipment, and then as we go along, we'll kind of address pricing too. But zinc wire seems to be a bit more of an affordable option. One other key point to mention, and this is related to temperature, is that zinc shouldn't be used in emergent service at temperatures above 140 degrees. So a good example for this would be, and again, it doesn't really have much of an impact on the bridge industry, but this would be a good option for potable water tanks, but definitely not for boilers that are going to see temperatures in excess of 140 degrees. So 8515, quite different, right? It costs about $1 or $2 more per square foot than pure zinc does. 8515, though, does combine the benefits of both pure zinc and pure aluminum. The alloy mix is denser, not thicker, and this is a distinction that's worth mentioning. So as basically, as you use 8515 versus aluminum, it uses about 20% more wire than pure zinc to cover the same square footage of steel. So it provides a denser coating, which means you use more of it to cover the same amount of square footage. So this is really where some of the cost comes from. This is maximum service temperature, as we talked about before, is 600 degrees Fahrenheit or 315 degrees Celsius. It's obviously much higher than zinc, but in terms of the bridge industry, that doesn't really mean a whole lot. 8515 can be used as a substitute for pure zinc because it's somewhat more chloride resistant while retaining good adhesion. And this is really the other distinguishing factor of aluminum versus zinc. If you take a look at the adhesion test results, you'll find that the adhesion for aluminum is a little bit higher than it is for zinc. But zinc certainly meets all the requirements that are necessary. So it's really just a question of what do you need, and do you feel like you need to go above and beyond what zinc can provide. So in all honesty, about a month ago, this slide wasn't even in here. And then 2 weeks ago, this slide was edited to say never used in bridge metallizing. And then a couple of days ago, or maybe a week ago, we decided to change this to rarely used in the bridge industry for metallizing. It's come to light, or at least it's come to my attention over the last couple of days, that there are actually a handful of bridges that were metallized using pure aluminum but it certainly isn't the norm. Sprayed aluminum is really preferred in the industrial or heavy manufacturing environments because, again, it can really handle extending the life of its substrate versus chemical or chemicals that would be found in an industrial sector in the atmosphere. Right, as you get more chemicals in the air, that certainly affects the corrosion rate, and aluminum certainly does a really good job of dealing with some of those chemicals. At elevated temperatures up to 1100 degrees Fahrenheit or 590 degrees centigrade, for example, on the fire side of a fossil fuel boiler tube, aluminum would be a really great choice. But again, for the ridge industry, we're basically just looking at outside temperature ranges that certainly we hope would never reach 1100 degrees. And finally, as we talk about materials, the question of sealers comes up quite a bit. Basically, a sealer is kind of a non-viscous liquid that's applied to the metallized surface to reduce the permeability of the coating and preserve the weight of the galvanic metallic coating. So if you're going to use a sealer, it's important to use a sealer of sufficiently low viscosity to get in and fill in any of the permeable little spots in the metallized coating. This is really the mechanism for how metallizing works. The zinc or alloy coating sacrifices itself over time, protecting the steel beneath. After many years, you reach a point where the zinc is no longer available in areas, exposing the underlying steel to corrosion. So there's two schools of thought on the use of a sealer with sprayed-on metallized coatings. First is to just apply the sealer after metallizing and allow it to preserve the weight of the galvanic metallic coating. No maintenance is needed for decades, but eventually, after 10, 20, 30 years, the sealer is going to break down. And in the meantime, when the sealer is in place, there's less metal is consumed by oxidation than if the metallic coating is left bare. Once the sealer is gone, then that's when the metallized coating starts to do its job by corroding slowly over time, protecting the steel. The sealer extends the life of the coating for the relatively low cost to apply the sealer. The second school of thought really is more sealer. You can add more sealer on a 10-year basis or so, or a 15-year basis or so to extend the life of the metallized surface below. And equally done in the field, and probably what we see more often is a lot of states just choose not to seal at all. And through all the research and studies that we've seen, 30 years with an unsealed metallized coating is not far off. It's not far off at all. It's pretty well expected. So in terms of achieving an indefinite service life, this is a picture of the Whittier Bridge that was metallized in Massachusetts. You could be looking at maybe a 10-year inspection cycle versus what you would find with paint, which could be, a much more frequent inspection cycle. So 10-year inspection cycle plus minor periodic maintenance. For example, cleaning. I mean, by minor periodic maintenance, I don't mean any recoating. I don't mean any reblasting. Essentially, anything you would do to maintain any bridge, whether it's steel or concrete, keeping the drains free, making sure the scuppers work, making sure there's no debris sitting on the bottom flanges or collecting water or soaking up water in any of the connection areas. By just doing that and nothing else, you're looking at a pretty good indefinite service life without any type of additional coating. The other thing to think about is eventually when the zinc is exhausted, whether you burn through the sealer and the metallized coating in 30, 40, 50 years, whatever it's going to be, you really then need to make a decision on what your next step is. Do you want to metallize it again in the sense that do you think that bridge is going to be in service for another 50 years? Was it originally designed for a 100-year lifespan? If you're only planning on having this bridge in service for 60 or 70 years total, at the end of that original metallizing life, you might want to consider other options if you don't necessarily have to protect the bridge for that long. So again, just another thing to keep in mind. So certainly sustainability is always something on the top of everybody's head. Sprayed zinc or aluminum contains no polluting volatile organic compounds or VOCs. It's worth mentioning that all the zinc splats that don't actually make it onto the steel, they're in the air. Some of them don't all stick. They actually fall to the ground and they're then collected and recycled. So just to give you an example of just one plant, in our own experience, in our Claremont, New Hampshire plant alone, we metallize about 1 million square feet of steel annually. So that results in maybe 50 or 60 tons of zinc that gets collected and recycled. So that's a pretty significant number. And obviously, if you look at that on the grand scheme of things and compare it to the number of thermal spray coaters and other fabricators that are doing this, it's a pretty significant number. So something to keep in mind. All this stuff gets recycled during the application process. The other important distinction to make is at the end of a bridge's life, at the end of a girder's life, when that girder gets melted down, all of that zinc or aluminum actually gets off-gassed and collected in the baghouse, and all of those materials also get collected and recycled and made into alloy wire or zinc wire or other zinc-based products. So zinc is recyclable both during the application process and certainly at the end of the life of a steel bridge. Other question that comes up often is, can you field apply metallizing? And the answer is yes. It's certainly an alternative to repainting. With painting, it's something to consider. Obviously, you need to be monitoring the atmospheric conditions that promote surface moisture. So temperature, not so much of an issue, but humidity certainly is something to consider. If you're going to field apply metallizing, you need to prepare the surface just like you would in the shop to SSP 10 near white as a minimum. To minimize flash rusting, you got to make sure everything's blast cleaned, vacuumed, and metallized on the same day. Again, in the shop we prefer 8 hours, but in the field things might differ. No temperature restrictions, no wait between coating layers, so there's no curing time or any waiting for things to dry. Keep in mind, though, that because this isn't a controlled environment like a shop would be, collecting and disposing of all that zinc can be really costly. So just something to keep in mind when making that decision. And how do you repair a metallized surface if it gets damaged? Just like anything else, you remove all the loose material and prepare the angular anchor tooth profile in accordance with SSP CSP 10. You'd feather the existing material around the damaged locations to prevent smooth transitions and maintain thickness of system and overlap areas. And this is really the key, and something Tony's going to mention in a little bit more detail as we look at some of the project examples. Getting a good, nice, smooth, aesthetically pleasing surface is easily achievable with an experienced applicator and really important to the performance. One of the other things to think about is metallizing is actually a really rugged and durable coating. So the likelihood of damaging a metallized surface in the field or through shipping is highly unlikely. The chances of that happening are pretty slim. So I'll turn it over to Tony. Tony will cover some of the project examples, and then we'll come back to talking a little bit more about what the industry is kind of looking at and doing to prepare for the future in terms of metallizing.
Thanks, Brian. We're going to give you a couple presentations or a couple examples of projects that have been successfully metallized and or painted and or tinted and or sealed, and give you a representation of what a well-coated system looks like in its final application. So, you know, Pawtucket River Bridge was a job that was metallized using 99% zinc, and a clear coat was tinted. And tinting means there's nothing more than adding a little bit of color to the clear coat. So in essence, what you ended up getting is a colorized bridge, and the owner, which is the Rhode Island Department of Transportation, took that into an advantage and ended up lighting the bridge and illuminating it in the evening hours, and it's quite spectacular as a finished product. So when you see something like this, you know, you have the ability to have a grayish color product. In this case, it ends up tinting a light blue and aesthetically pleasing to the eye. Project was fairly substantial in size. Some of the units there that we fabricated in the box sections, you know, were as heavy as 25 and 30 tons. So getting those into a hot dip bath is pretty difficult to do. So metallizing was used and was applied at in a volume of about 10 to 12 mils, and like I said, seal coated and erected. There was no touch up in the field. The job went fairly smooth, so gives you an idea what the underside of the bridge looks like, and there's a walkway underneath there. Providence Bridge was a project in, again, Rhode Island, Massachusetts, Connecticut, New York have been using metallization for several years, quite a few years. And one of the advantages of having a metallized bridge erected off-site, fully coated, and you have a bridge that, in this case, was metallized and fully painted. And erected off-site, any damage that was done was easily correctable in the field before it went to the site. It's a very inaccessible project to deal with after the fact. So the owner and the contractor decided to use metallization and paint, floated in, and dropped it into place. That's the finished project and the structure over there. It's a fairly impressive area. It's a very, very high use port, so setting up blast operations at the site was not acceptable for this project. The Memorial Bridge up in Kittery, Maine, going to Portsmouth, New Hampshire, is an example of a very highly corrosive area where metallization was chosen. In many aspects, you have almost a daily salt fog coming in off the ocean. So you have a metallized product here in the lower quartz sections that was applied as much as 14 mils, and in several instances on the back ends that there were as much as 20 mils of material applied, and was seal coated. So it's performed well over the last 3 or 4 years. No significant loss, and maintains a very unique and similar profile across the towers as well as the main lift span itself. This is also one of the bridges here that of interest was the original specification of the bridge was a 3-coat paint system, and because of the loading of the snow on the walkways and the lower chords, the DOT examined the metallization as an alternative to the 3-coat system for longevity as well as maintenance, and after careful consideration they ended up using the metallizing process versus a fully painted system.
I think another important thing to mention too is I think the University of New Hampshire is doing a study on the bridge life, right? So they've got a whole bunch of instrumentation on the bridge to measure a whole lot of things: vibration, tidal influence on the substructure, but related to metallizing, they've got sensors in place to regularly measure the metallization thickness. And after a couple of years, there's been no change in any of the thickness so far. It's performing as expected. So we're happy about that.
Yep. And another representation of a fully metallized structure using 8515 is up in Lake Champlain. That job was metallized with 8515, fairly substantial tied arch, and with a clear coat applied. And it's a very, very, very pleasant looking structure, and it's performing in a very, very pristine area up in the river and in the Finger Lakes region, up in New York and Vermont, and looks to expect a 50-year life with no maintenance.
Great. So I'm going to play this video for you on slip critical connections as I go through this. Any additional coating over metallized surfaces has to meet a Class B requirement for slip critical connections, or you'll have to mask the connection, which drives up the cost. AASHTO requires the slip critical connection to meet Class B, which essentially provides a minimum of 0.5 slip coefficient. Typically, the engineer has to select a frictional slip coefficient between the layers of a connection to calculate the slip resistance. I'll go back to this as I go on. So according to FHWA, coating must be compatible with use in high-strength bolt connections. We covered that. A really important thing to take note of is the fact that in 2014, FHWA published this tech brief on slip and creep of thermal spray coatings. The research was carried out by KTA, and ultimately their conclusion was that unsealed metallized surfaces meet Class B slip requirements. So we'll move on to talk about what, as an industry, we're doing related to metallizing. As many of you know, the AASHTO-NSBA Steel Collaboration exists. Their mission is to provide a forum for professionals where they can work together to improve and achieve the quality and value of steel bridges through standardization of design, fabrication, and erection. This is exactly what has been taking place in their task group number 8, or TG8, that focuses on coatings. Over the years, primarily TG8 is focused on a lot of initiatives that have dealt with paint and paint systems. But in recent times, based on the interest and demand that has been voiced by the industry, their next focus is on developing a nationally recognized guide specification on metallization, or metallizing. And this is really important, right? I mean, we want to make sure that as an industry, we can provide good quality products. We can provide good quality based on what our fabricators are doing. So this is a great collaborative effort between industry and the states and owners and the engineering community to figure out what that we can do to protect steel from corrosion. So there's quite a few things that TG8 covers, and I'll kind of go through a list of what they've done and give you an update on where we're at. Recently, NSBA completed a fabricator survey on metallizing. They also completed a DOT survey on metallizing and galvanizing with a response of 34 states. So that's actually a really good response rate from 50 states in the district. Most of the DOT support a proposed guide spec for metallizing and said they'd adopt it. So this is really important, right? 34 states responded. 7 states said that they already have a section in their state spec on metallizing. But even more important than that, 27 states indicated that they would adopt an AASHTO-NSBA guide specification on metallizing if it was complete, if and when it was completed. And the if is not really an issue. In fact, after the last meeting in Denver, I think the draft is already underway. I know it's an aggressive schedule, but they were shooting to have the first draft of the specification complete by January. And to give you a sense for the cross-section of folks that are involved in TG8, you have a whole lot of state DOT representatives, you have metallizing inspectors, you have thermal spray applicators, you've got fabricators that do their own in-house metallizing. The other interesting point that I found out a little bit later, because I was kind of curious to know how those states broke down in terms of using zinc or zinc aluminum 8515. 2 states that have a spec allow all 3 flavors of metallizing, so zinc, 8515, and aluminum. 2 states allowed zinc and they allowed 8515, and 2 states allowed 8515 only. So there's no consensus. And again, this is another reason and a good platform for states and the design community and the fabrication community to come together to have a really good in-depth discussion about what's needed and what works best and share some of that information. So I think the collaboration has done a really good job of this. In terms of some additional information, some things to keep in mind in terms of resources, you can Google and find all of these things on the web. That slip and creep of thermal spray coatings, that FHW tech brief, was authored by Dr. Justin Osell back in October of 2014. ISO 2063 is another standard that relates to metallizing. And SSPC CS 23.00 or AWS C2.23M and NACE number 12. These are all standards that all relate to metallizing within our industry. And I would also say with the World Steel, well, NASCC is coming up in April, which is co-locating with NSBA's World Steel Bridge Symposium. I can tell you for certain that there's already one session that's talking about corrosion protection and metallizing, and we're discussing the opportunity to put a panel discussion together with a whole bunch of participants, maybe even some of the folks on TG8 that will get together to have this discussion in person and hash out some of these details. So I think we're headed in a good direction. This hopefully gives you a pretty good basic understanding for metallizing and how it's applied, what's used, some of the things to consider when using it, or at least thinking about using it. I think at this point, Matt, we're ready to move into the question and answer period. I know Matt's been kind of scouring the chat box, so I will turn it over to you, and maybe we can take some questions.
Yeah, thanks, Brian, and thanks, Tony. We have a number of questions that have come in. Feel free to keep adding to the questions. You still have time to get them in. We have a fair amount of time, so we should be able to cover most of them. The first question that came in talks about addressing inaccessible areas, so kind of around stiffeners, acute angles, getting in between plates. How do you apply metallizing to those kind of hard-to-reach areas?
The actual process to maintain and I'll say repair that area is fairly simple. We apply zinc, organic zinc property to it, and same issues that we encounter with metallization you encounter painting. So you basically have to apply organic zinc product to those areas that are very difficult to reach. You know, especially the snipe areas are very, very difficult to reach. And a simple repair, typically also in a damaged area, does not necessarily have to be repaired with a metallized product. It can be repaired utilizing the organic zinc process and coated similarly to what typically the rest of the bridge is either painted or sealed with, and you'll have the same finish appearance.
Okay, great. We have another question here that deals with qualifications. Are the applicator qualifications per NACE or SSPC?
We find that either are acceptable, and we recommend that any applier has either NACE certification or the SSPC certifications. Or the sophisticated paint endorsement certifications on hand before attempting to metallize any products. Without the proper experience in handling the application, you'll have a very, very difficult task at hand in developing the profiles required for the anchorage as well as the uniformity of the application.
Okay, great. We've had a number of questions come in regarding kind of a duplex coating system and the ability to paint over metallizing. Looks like some people realize you can paint over galvanizing, but they're unsure of if you can paint over metallizing.
It's the sealer coat, typically is a paint system. Which is rarely used, and when no surface prep needs to be done, as long as it's applied prior to certain criteria of time, a sealer coat and intermediate coat as well as a finish coat can be applied to the metallized surfaces with very, very few problems.
As a follow-up to that question, are there any specifications available that someone should be referencing if they want to do something like that?
There's many recommendations that are out in the marketplace right now as far as millages and tolerances. I think the best situation at hand is to look what recommendations there are on with NACE as far as the application thicknesses and profiles. This gives you a very, very uniform product that the industry can control and apply to.
And I think this is one of the most important key points that TG8 is trying to come up with, is a consensus on the minimum and maximum acceptable ranges for both the blast or for the metallized surface. So that draft will be out in January, and hopefully we'll have some more definitive information from the collaboration.
Okay, great. I had a few questions regarding the weight per square foot of the metallizing product, and maybe you want to break it down based upon the different materials, so the 99% zinc, the 8515, and the 99 aluminum, if you happen to know that.
Offhand, don't have that, but that's going to vary depending on the thickness of application. If you're applying a 8 to 14 mil profile, it's going to vary if you're going to apply a 14 to and greater, but I'm not 100% sure, but I think it's roughly an ounce per square inch per a 8 to 10 mil applications. It's not. We're not putting a very, very deep coat of zinc on the product. It's really not a very heavy product at all.
All right. We have a few questions regarding the life cycle cost comparison. So I'll start it off with, do you happen to know the oldest bridge that has been metallized, and have they been doing any long-term studies on the performance of the metallizing on that bridge?
In the U.S., we've had several bridges only in actual full performance, really in less than 20 years. I don't think any individual study has been done on a specific bridge. That's why I think the Memorial Bridge in New Hampshire is being studied like it is to understand exactly how the performance of the zinc will be affected over time. The FHWA published a 30-year study based on application, non-bridge application, and show that either 99% or 85% zinc really has performed outstandingly over a 30-year lifespan. And that was published last October 14.
As a follow-up, can you discuss the life cycle cost comparison between metallizing and a 3-coat paint system?
Well, I'm not sure about the full life cycle cost. I mean, I can say it's probably fair to say that if you're going to have a bridge metallized by a third party applicator, you're probably looking at a range of maybe $12 to $14 per square foot. If you're dealing with a fabricator that has its own in-house capabilities and has the experience and has kind of ramped up the learning curve, I would say that's right in line with what you would pay for a 3-coat paint system. It's pretty competitive with paint if you've got somebody that does it in-house and knows what they're doing, because really that extra cost comes from a third party coming in and mobilizing their cabinets and mobilizing all of those folks in your shop to metallize. And again, it's not a quick process. It takes a little bit of time.
Okay, great. We have one question here. Can you use hot-dipped galvanized connections with sprayed aluminum coatings on the members? So can we mix galvanized members and I guess a metallized plate girder system?
Mix you can have a main load carrying member, metallized, and depending on your connection and what you're designing your connection to, you can have your secondary members tie into that are hot dip galvanized with no issue. But if the question is, can you apply 8515 or zinc to the hot dip galvanizing? I don't think that's doable.
I don't know.
Never seen that happen.
That's one thing that I forgot to mention before. We did talk about no size limitations, and certainly metallizing is a really good fit for bridge girders. But for things like cross frames and things that are smaller, it doesn't it doesn't really pay to metallize those. I mean, sending those cross frames out to the galvanizer and having those things dipped are a perfect complement to metallizing some of the larger components of a bridge.
Okay, great. We got a couple more minutes. We might be able to fit a few more questions in. One here, what is the prep process for repainting over metallizing? And can you get full paint life without blasting, damaging the metallizing that remains? And is there what spec might apply? So it's kind of a three-part question.
A lot of that depends upon the actual paint system that's specified and the life of the consumption of the paint over time. There are several paint systems currently on the market that can actually be power washed and recoated without any blasting at all. So I think you have to study what the specific needs of that job are and really look at the long term. But there definitely are paints that are consumed, power washed and recoated without ever touching the metallization. So if you're going to do the best system that you possibly can, that would be the system that you would want to research. And actually, that's you saw one of the structures there that have been recently done, the Whittier Bridge up in Massachusetts. That is a system that has that three-part paint system on top of the metallizing that the paint would be consumed and over time, and then a power wash and a recoat, which basically would give it theoretically a 100-year lifespan without touching the metallization.
Okay, we have an interesting question here. Can you have a member that is in contact with water that has been metallized?
I think the FHWA's paper that was written had to do with actually a metallized product that was submerged.
Yeah, and you'd certainly see the U.S. Navy has been using metallizing for their ship hulls for decades. Metallizing may not necessarily be exactly the same specifications or the same exact materials, but yeah, metallizing has been used in shipbuilding for decades. You'll also see it on submerged piles that are in mud or in water. So yeah, I would say metallizing certainly is an option for submerged situations.
Okay, great. Well, unfortunately, we are butting up against the top of the hour right here. So I would like to thank you, Brian, and thank you, Tony, for being with us.